Okay, so I believe in the last class you guys were introduced to the differential amplifier. So just to give a recap, I guess you started with something like this. And you had a resistively loaded differential pair. Now to increase the gain, instead of using a resistor, what is the thought process? What do you use? Yeah, it's the active load. So in principle, if you are given any choice, what would you put instead of a resistor? I give you an access to all possible electrical elements you have. What would be the most ideal thing you put in place of a resistor? Current source. Okay, current source is what you want to do, and you try to realize current source using transistor. And would you use an NMOS transistor or a PMOS transistor here? PMOS. So that's what you do. Sorry, this. And of course, to make sure that the PMOS carries the correct current, you need to bias this voltage. And how did you generate this bias voltage without any redundancy? You kind of do this connection and you tap this point and call as the output, right? And I think you guys also calculated the differential mode gain. So if I give plus VDM and minus VDM here, you know how to calculate the small signal gain. And of course, you can do it in a couple of ways. One, you can basically find the small signal currents and do blah blah blah. Other thing you can also do for, let us say, slightly complicated circuits is, see, this circuit for small signals, is it a linear circuit or a non-linear circuit? Small signal, linear circuit. If I have any linear network like this, containing all linear components, resistors, whatever, capacitors, inductors, control sources and so on, and let us say there is some independent voltage source like this, and this is the output. What is the simplest way to model this entire network? Thevenin equivalent. So you either have an equivalent open circuit voltage source and an equivalent RTH, or a current source in parallel with the same resistance. So here this is also a linear circuit like this. So in principle you can find the Norton equivalent current, find the equivalent Thevenin resistance. To find the output voltage, I just take the product of these two fellows. And to find the Norton current, what would you do typically? This is the network, right? If you want to find the Norton current, what would you measure? You basically short circuit the output side. That should make sense, because if I short circuit this, all of this current flows here. So you find the short circuit current, that gives the Norton current, and you find the effective resistance looking in, that gives the resistance, and you take the product, right? That's also something you can do. So now let's try to calculate the differential mode gain for this. I'm sure it was done. Let's just quickly go through this. So for small signals, what happens to the tail current source? Open. Great. What happens to the supply here? Awesome. So if I do that, what can you, let's assume a simpler case wherein I'll take lambda only for the PMOS, and for the NMOS let's assume that lambda is 0. So what is this voltage tail node Vs? Why was it 0? What is virtual ground? Sorry? Yeah, of course. See, when I draw things like this, the left and the transistors on the left and the corresponding one on the right have identical dimensions. Okay, unless otherwise mentioned. Yeah. So what is Vs? You told 0, but why 0? If you don't know, how do you find it? You do the KCL, whatever. So what is the small signal current flowing here? Gm of the NMOS times VGS, which is VDM minus Vs. What is the current in this transistor? For this transistor it is GM times VGS of this transistor. For this transistor, it should be GM VGS of that transistor, right? So if I do that, I'll have GMN. So unstable this one. And what is the current flowing here? Open circuit, what is the current? 0. So if I solve for it, what do you get? Right? Now, of course, you get this result. Let's try to quickly make some sense of this. Now, let us say I gave you this circuit, something you might have seen already. The same diff pair with a resistive load. Again, purely differential mode excitation like this. And let us say in this case, I even consider the lambda for the NMOS. In this case, what can you say about this voltage? Okay, why not 0? I mean, which resistance? Which resistance are you talking about? Okay, but if you look at the circuit, how does the circuit look like visually? Symmetric circuit, and for small signals, this is linear or non-linear? So loosely speaking, or I mean not loosely speaking, I can think of it like this. Left side I have a linear network, right side I have the same fellow. So this is one linear network N, another linear network, a symmetrical version, and this is put like this, and this is this node Vs. And here I am applying, let us say, plus V and minus V. What will be this potential? Right? I am sure this was covered. Please recollect. And why is this 0? What makes this equal to exactly 0? So where is symmetry being used here? Or let's say, how do you prove this to be equal to 0 exactly? Let's say I give you this, ask to find this voltage. What would you do? Correct. Okay, linear network, I have two inputs. What would you do? Superposition. Let us say due to the positive input, you ground this fellow. If this is V, what will be Vs in terms of V? I mean, this is a linear network. I give an input voltage V. How will be the output voltage be related to the input voltage? It's a linear network. Why it's called linear? Because things are all linear, so this is going to be some alpha times V. Now, if you find the response due to the other fellow, you ground this and apply minus V here. Now, what will be the response due to the minus V? Same. It's just I put a mirror and flipped it around, so it's minus V 0. Okay. So I'm sure this is. Please recollect. Yeah. So if you have a symmetrical network like this, and if the circuit is linear, all the nodes along the line of symmetry, they will be at 0. So this is something you know. Now look at this circuit. Is it symmetrical or asymmetrical? Asymmetrical. But here also you see that under this condition, when I ignore the lambda for the NMOS, this tail node is at 0. So why do you think that makes sense? Or does it make sense at all? Of course, it comes out of the math, but from this result and the fact that lambda is not considered for the NMOS, can you kind of argue that this must be 0? Okay, think of it like this. In this circuit, which part is making this network asymmetrical? The upper PMOS. And what I have done, I have ignored the lambda for NMOS. If lambda is 0, what does it mean? RDS is 0. In other words, the drain current, does it depend on the drain voltage? Right? So in this, I see that whatever happens at these two nodes have no bearing to whatever happens in this point. Fine. So now if I just look at this part of the network, it looks like whatever happens here has no relation to what happens here. So it's as though this part is not there. So this looks symmetrical. Right? I mean, we can also do this way, right? So let us say if I quickly draw the small signal for this. So let's say use this color. This is the voltage control current source for the left transistor, for the right transistor. This is the whatever, right? So this is the small signal equivalent for this. Fine. Now I have ignored that lambda is 0, so which means only the current source is going to be there, and then at the top I'll have something. Now I know for a fact that these two are not same, right? So this will be some network A, some network B. Okay, but remember that I have a current source, and whatever is asymmetrical, that is actually coming in series with the current source. Now if I have a current source and I put something in series to it, do you think the current changes? Right? Similarly, if I have a voltage source and I put anything in parallel to it, does the voltage change? Right? So because we have ignored lambda, this is like an ideal current source. So it doesn't matter what I connect here, it doesn't get affected. So for argument's sake, I can even say that this is not even there. Right? Even if it's not there, the bottom part of the circuit is going to function the same way. And now with respect to the bottom half, the network is obviously symmetrical. So it makes sense that even this node should be 0. So again, it is the same argument of symmetry, and here you can invoke this because we have ignored the channel length modulation for the NMOS. So it's a nice interview question. I mean, you can ask like, is there any condition by which this asymmetrical circuit can be thought of as symmetrical? And this is one kind of scenario where this can happen. Cool. So is this point clear? So now let's get back to the calculation. Copy this. Yeah, so now I know the tail node voltage is incrementally 0. So what is the small signal current I1? Gm of the NMOS times the gate to source voltage, which in this case is just VDM. Fine. What can you say about the small signal current here? Yeah, if you try to find I2, that will be minus of this. So I can basically say that the current flowing up is, and that should also make sense because here I have open circuit. Whatever current is flowing here, the only path for it to flow is here. So what can you say about the current in the PMOS transistor? If the current flowing here is I1, what will be the current flowing here? Same. So remember, this is a PMOS current mirror. So what can you say about this current? I1. Fine. It's a current mirror. This will faithfully replicate whatever current was there in the diode connected branch. So what is the total current that is pushed out of this node? 2 times I1. And of course, if you try to find the Norton short circuit current, you will basically short circuit this. The short circuit current will be indeed 2 times I1. So the total, maybe I'll write it here, the Norton current will be 2 times I1, which is 2 GMN times VDM, or I'll write it like this, GMN times 2 times the differential, 2 times VDM. So this is the total current that will be pushed out, and that current flows through the effective impedance at this node to generate the output voltage. And what is the effective resistance looking here? Remember, lambda is 0 for the NMOS. So looking down, it's basically an open circuit. So what is the effective resistance here? Yeah, whatever is there for the PMOS, and what is that? Is it, at this node, I can have, I have NMOS and PMOS. What we have assumed is NMOS has no lambda. So any change you make at this point will result in 0 current here. So this is as though it's open with respect to the impedance calculation. So I only have the PMOS, And what is the effective resistance looking into the drain of the PMOS transistor? RDS of the PMOS transistor. So I'll maybe write this. The output resistance is RDS of the PMOS. So the total output is a product of this. This is GMN RDSP times 2 times VDM. So what is the differential mode gain now? I mean, what is the gain for differential mode signals? GMN times? Fine. 2 VDM is the differential mode input you have applied, whatever, output input. Okay. Cool. So now, so I think this point was already covered. The gain was covered. I'm just revising it. So now let me actually copy this. So now if you actually see here, let us say, yeah, this is the diff amp that we considered. Here if I look at the effective short circuit current or the total current that flows into the output, what is the total current? You just calculate it. Yeah, 2 times I1. I1 is basically GMN times 2 times. Fine. Now let us say instead of doing this, you did the following. Just give me a moment. Let me make some space and draw this. So let us say instead of doing this, you did the following. That is, you have the differential pair, right? Now remember, I just want the output, single-ended output. So let us say you say that I am going to tap the output only from here. I will just put the current source only for this fellow, and then I can also do this. Fine. This is also fine. So by the way, here under what condition I can say that the source voltage is 0, the tail node voltage is 0? Lambda? Yeah, again, if I ignore the lambda for the NMOS, so I will write it here, the condition we have considered is this. So here again, if you ignore the lambda for the NMOS, again, this is kind of symmetrical because whatever happens at this node has no effect on the tail node. So we can say this. So in this case, if I find the total short circuit output current, what will that be? This is the output, right? How much will that be? Okay, let's find it. What will be the, this is 0, remember. What will be the current flowing here? Huh? GM times VDM, fine. What is the current flowing here? GM times VDM. So what will be the total current that will flow? Basically, assume that I am finding the Norton equivalent current. So I am short circuiting the output. What will be the effective current that will flow? Yeah, the same current, right? So what is the current that is flowing? GMN times VDM. Fine. And you see it's 2 times smaller than what we have in our circuit, right? Now, similarly, you can also do the following. So you can also make a diff amp to get a single-ended output this way also. Let me see if I can maybe reduce the size. I can just do this also, right? I will generate this bias voltage somewhere else and I apply it here. Instead of making that diode connection, I will just say I put 2 current sources and both of them are biased to some voltage. I will generate that voltage somewhere. I don't care. So now in this case, first of all, let's say even if I have lambda for both NMOS and PMOS, what can you say about this voltage? Why? This circuit is purely symmetrical. So as long as I have anti-symmetrical excitations, that is a differential mode input like this, plus V minus V, again all the nodes along the line of symmetry will be 0. So in this case, if I find the short circuit current, what will that be? Yeah, if I again, let's say I short this, I'll have currents obviously flowing in both these fellows, but whatever current is flowing here will not affect my output, only this current will flow to the output. So here also it is a factor of 2 smaller. Okay, is this clear? So for a long time, when people had to make an op amp, and remember the classic op amp that people wanted to sell in the earlier times was this. It needs to take in 2 inputs, provide a single-ended output like this, right? So you can take the difference between the 2 inputs using this, the differential pair. To get the single-ended output, people were always doing something like this, right? So here you see both these transistors here, they are providing a small signal current. The currents in both the transistors are dependent on the differential voltage that you apply. But in these 2 cases, you are completely discarding the current in this branch and only utilizing the current in this branch, right? This is basically, it is there, but you are not using the current from the transistor. So that is why you are kind of not getting the full possible whatever, right? You are not utilizing its full potential. Whereas in our circuit, what we have done is, we are having currents in both the transistors, but instead of discarding the current in this fellow, we are actually passing it through a current mirror, making sure that current is also copied and added at the output. Fine. So that is why the total current or the total gain in this case is 2 times larger than these 2 cases. Yeah. And it turns out this was actually discovered or invented in the late 1960s or early 70s by Bob Widlar. I don't know if you guys, has anyone heard Widlar current source or something, current mirror? Yeah, so he was a prolific and a crazy circuit designer. Okay, and I think I have some pictures. So he's the guy. So I mean, he was so prolific that the companies in which he worked were Fairchild Semiconductors and National Semiconductors. So it said that any circuit he designed had so much of innovation that because of him, the products of those 2 companies were the top sellers, and they were the leading companies of electronics at the time. And of course, now Fairchild is with onsemi and National Semiconductors is with TI. But yeah, and it said that I think he designed one. I think he was the first person to design a commercial op amp, right? Whatever op amps companies are selling you, the very first or one of the earlier prototypes that was sold was designed by him. And it is said that there was one op amp which he designed, LM10 or something, and for the next 10 years, no other company was able to match that spec. Okay. So some crazy fellow. And see if you have. Yeah, it's another picture. Yeah. Anyways, cool. Yeah, but since he introduced this thing, this has been the de facto standard of realizing a single stage op amp, or anytime you want to have a case where you sense the difference between 2 signals and get a single-ended output. This is the circuit that we are using and we will be using, because this is the most efficient and optimal solution we can get. So let me just summarize this. So we have this fellow, and here we saw that the differential mode gain is Gm of the NMOS times the RDS of the PMOS. Fine. Cool. Now let us say I add an output resistor here. Let me erase this. That is, I add a load resistor here, RL, and should I be connecting this directly to the output here, or should I do something? I should put a capacitor so that the DC operating point doesn't change. We have not looked at the DC operating point of this yet, but we'll come to that later. So if I put a load resistor, what happens to the gain? Does it remain the same or it changes? The load resistor is appearing in parallel to whatever resistance was there, so it's going to change like this. Now remember that if I say that I want to make an op amp, this is what you want to do. Now an op amp is what kind of a control source? Voltage control? Voltage source. So at the output side it is behaving like a voltage source, right? So which means if I go and connect any load at the output, do you think the voltage should change? It's a voltage source. I say if you put an elephant across the voltage source also, the voltage source will maintain that voltage across that elephant. Nothing should change. But here you see I put a load resistor and suddenly the output completely changes. So strictly speaking, this is not a voltage controlled voltage source. It turns out what we have realized is a voltage controlled current source. Okay. Because here if I try to find the short circuit current, that is going to be same whatever we calculated irrespective of whatever I have connected at this point. Okay. So what we have designed is VCCS. So this is no longer a true operational amplifier. What we have is often called as the operational transconductance amplifier. We call this as OTA. And of course for op amp this is the symbol. So we have OTA, we need to have a new symbol, and the symbol is basically a quadrilateral instead of a triangle. So the idea is the output current of this block will be constant and it will depend only on the differential voltage you have applied, right? So the parameter is the transconductance or GM, and this will have its own output resistance. Okay. So in our 5 transistor or in this op amp or in this OTA, if I find the short circuit current, what was that equal to? Yeah, 2I1, but what was I1? GMN times 2 times VDM was the current. So if I basically I'm trying to find the transconductance of this thing, right? So what we are doing is this, I'm trying to find GM. That is, I want to model this like this, okay? So I'm trying to find the GM, and the simplest test setup you can do is this, you apply a voltage here and you short circuit the output. What will be the current that will flow? Okay, maybe I didn't explain it clearly. So when I say it's OTA, what it means is if I apply a voltage V, the current I out is basically GM times. So, is it fine? Similarly for an op amp, if I apply a voltage V and if it has a gain of A, the output voltage is A times V, that's all. So here now I am trying to find the GM. So which means I should somehow measure this current. The simplest way to measure the current is to make it pass through a short circuit so that all the current is kind of extracted, and then you find the current divided by the applied voltage, that gives the GM. So basically what I am saying is we define GM as I out by the applied voltage. So if I do this experiment in this circuit, maybe I'll copy paste it separately. Yeah. So I am trying to find the short circuit current in this circuit, and what was the short circuit current equal to? GM into VDM or 2 VDM? 2 VDM. So to find the GM here, I should take the difference between the short circuit current by the differential voltage you apply, which is 2 VDM. That is basically the GM of the NMOS. Shouldn't be surprising because this transistor is what is taking the voltage and converting it to current. It's not surprising, but just for the sake of completeness, I did that. And similarly, if you try to find the output resistance, here we already saw this was basically the RDS of the PMOS. Okay. Right. So in practice, on chip, whenever we say it's op amp, it is all cheating, it is all OTA. No one designs op amp strictly, on chip especially. So it is all an operational transconductance amplifier. So only if you are designing a separate product for an op amp, you make it like a voltage source. Otherwise, on chip, it is all an OTA. Okay. And this is often called the 5 transistor OTA. Or some people also call this the 5-pack OTA. So if you go to gym and practice regularly, you'll get 6 packs. If you go to your analog circuits class and practice regularly, you'll understand 5-pack OTA. Okay. Cool. So now we have seen this. Oh yeah, okay, good point. Yeah. Why did I call it 5? Where is the 5th transistor? See, no one asked. Good. Yeah. Remember that this ideal current source. Ideal current source is only available in textbooks and simulators. So this will finally be replaced by. Yeah, good point. Yes. Okay. Yeah. So the deal is this. So this is the 5 transistor OTA, and as I mentioned, this is the most commonly used or the default circuit used for getting a single-ended output. Okay. And this basic structure is the differential pair, what I am highlighting in green, and it is the I would say the fundamental building block of modern analog circuits. When I say analog circuits, it is RF, mixed signal, everything. Okay. So if you want to be good at analog circuits, you better be very comfortable and have a good understanding of this differential pair. Okay. Cool. So any questions? Okay.
So what will be the bias voltage of this?
Yeah, we'll come to the bias points in the next class, right? But I mean, you are this voltage. Yeah, this will be grounded, correct. For now, let's assume it's an ideal current source, okay? See, you know how to make a current source, right? If this current source is not good, what can you do? You can use a cascode, right? This is the simplest thing, but if you want this to be a better current source, you can put a cascode, or you can put one more cascode, and whatever you want, right? I mean,
What if lambda is not equal?
Lambda of which one? Okay. You're saying we didn't consider lambda for the NMOS, right? Yeah. The deal is the moment you consider the lambda for the NMOS, analysis is not that trivial. But see, logically speaking, for this case, we know that Vs is exactly 0. That is, when lambda n is 0, I know that tail node is exactly 0. When lambda n is not 0, can you make any statement about Vs? It won't be exactly 0, but any reasonable approximation you can make? It will be close to 0, right? I mean, it is not as though, it is not like it's a discontinuity, right? It is not like exactly at lambda equal to 0, it is 0, and for any value that is away from 0, it's going to shoot up, right? For reasonable values of lambda, can still be approximated as 0, but exact calculation becomes messy, so that's why when you introduce it, I don't consider it. Cool. And yeah, for this one we have already seen the differential mode gain, and that was GM of the NMOS times the RDS of the PMOS. Now we have found the differential mode gain. What is the next thing to do? Common mode gain. So let's do that. So okay, maybe I'll draw this again. Again, for initial assumption, initial calculations, we'll assume we have an ideal current source. So let's not complicate unnecessarily. Okay. Oh, and actually, before that, before going to the common mode gain, right? So let me, I know this is my output, and I can model this fellow as an OTA like this. Fine. So I know this is the output, but what is the plus terminal, minus terminal here? I have two, right? A and B. Which is the plus terminal and which is the minus terminal? Yeah, why? Let's say you don't know, how do you find it? Yeah, let's see. Let us say you increase A. What will happen to this potential? It's all small signals, right? You make a small signal increase to the gate voltage. What will happen to the drain voltage? Increase or decrease? Decrease. Fine. Why decrease? Yeah, current is going to get pulled out. The moment you pull out current, voltage is going to drop, and the gate voltage is also reducing. Gate voltage is reducing, the drain voltage will. So which is the plus terminal? A is plus terminal. So this is going to be the plus terminal. This will be the minus terminal. Okay, so now let's continue with the common mode gain calculation. So let's say I have a common mode signal, DCM. I am interested to find what will happen to the output. That is, both the gate voltages are increased slightly by the same amount, and I want to see how much will be the corresponding change in the output voltage. That is the exercise. So let me copy this and maybe draw the small signal here. So for small signal, current source is open, the voltage source supply is short. So can you tell me what is the source voltage? Yeah, why? So? Yeah, okay, again, so let me say the assumptions. The assumptions are the same as before. Lambda for the NMOS is still not considered, okay? Yeah, and in that case, as he is pointing out, if you basically draw the small signal equivalent, you will have only the voltage controlled current source for the two transistors. There is no RDS, and remember that there is no path for the current to flow, open circuit. So sum of the two currents will be 0, and both the currents are equal, obviously, right? So the current flowing in the left side plus the current flowing in the right side, they should be 0. And the left side current is equal to right side current, so that only means that current is 0. So if the current is 0, the source voltage is also equal to the gate voltage, right? GM VGS is the current, VGS has to be 0 for the current to be 0. So I know that the incremental current in the transistors, how much is there? How much is it? What is the incremental current? 0. Oops. 0. So 0 current flows here, 0 current flows here. So what is the small signal output then? 0. 0 current flows, it results in 0 voltage. So what is the common mode gain? How much? 0. Is this clear? So now tell me, do you think will it be 0 exactly, or in practice what will make it non-zero? What non-ideality will make this non-zero? Lambda of what? Okay, let's say even lambda is considered also, right? Do you think anything will change? Even if lambda is there, what can you say about the small signal currents in the two transistors? No, will they be same or different? The gate voltage is same, source voltage is same. Even if I have channel length modulation, the total current or okay, maybe I made a mistake. So let us say lambda is there, what will happen? Sorry, I made a mistake. If lambda n is present, you are right, it will be there. But let us say lambda n is fine. Is there anything else? Resistance of? Yeah, that this is the main kind of deal, right? Because we have an open circuit is what we say, is why we saw that the sum of the currents is 0. Okay, so this will be, this tail current source will have a severe effect than the lambdas of the transistors. Okay, so now let's assume that this tail current source is not ideal. So to incorporate the non-ideality of the tail current source, what should I change in the circuit? I'll just have a small signal resistance. So let me do that. So maybe I'll call it say yeah, say RSS or something. Maybe I'll just say RX. So now can you calculate and tell me what is Vs? Again, lambda of the NMOS is not considered. So can you find and tell me what is Vs? Huh? No, in terms of the input and the transistor parameters, that's all, right? I mean, just work out and tell me, right? If you're not able to say it by inspection, it's completely fine. No one will be able to just look at it and say in the first go. You solve it, see the result and try to make sense of it. Okay, can you slow? 2? Of which transistor? NMOS. Into VCM, I believe, by 1 plus 2 GM and RSS. That this doesn't look correct to me. Correct. This seems about right. I mean, you can basically write KCL and get this, but let's try to get this. Yeah, let's try to get this in a different way, directly maybe. See, again I can consider the setup like this. I have a linear circuit, small signal linear circuit. I have 2 excitations. So how can I solve for this? A linear circuit, I have 2 inputs. What do I do? Let's say use superposition. Let's say this is not there. Fine. So maybe I'll use a different color. Let's say this is grounded, right? So what is the looking in resistance here? Remember that the lambda for the transistor is 0. I am looking into the source of the transistor. How much is that impedance? 1 by GM. Is that fine? If not, please work out. These are some simple results that you should remember. Okay. So now I can basically redraw the circuit like this. Okay, maybe I'll take to a second page. Take some space here. Okay. So I have the left side NMOS transistor wherein the input is applied. I have Rx, fine, and the looking in resistance is 1 by Gm. So it's basically effectively adding a resistance of, right? Now I'm applying an input at the gate, finding the voltage from the source. Do you know the result already? I'm applying the voltage at the gate. I'm trying to measure the voltage from the source of the transistor. What kind of a configuration is this? Source follower. So what is the voltage gain for source follower? Gm into Gm of the NMOS times? Yeah, whatever resistance you have here, please recollect. Again, these are simple results to remember. If again lambda of this is 0, then if I apply Vi, this is V0 and this is R. V0 by Vi is what? Fine. Hopefully it is not really alien. You might have, this rings a bell somehow. Huh? And in our circuit, what is R? Rx parallel this. So let's do that. Rx parallel 1 by Gmn by 1 plus the same thing. So you simplify this, you get Gmn times Rx by 1 plus 2 Gmn into Rx times Vc. So this is just the half, this is just half the picture, because right now we have considered the effect of this input, found the output here. What will be the effect due to this input here? It will be same. So what will be the total output? 2 times of this. Okay. So we did superposition. So we only consider the signal applied at the left side transistor. We found what is the output. Now to finish the process, I need to short this, apply VCM to the right side transistor, find Vs, and it's obvious that this is going to be same. So the total result is sum of the two. So we'll find that Vs is 2 times this. That's what I think you also got. Okay. So yeah. Let me copy this.
Here we can also consider Rx like 2Rx in parallel with 2Rx. Can we use symmetry to solve it?
No, the thing is, it is not completely symmetrical because of this connection. But yeah, in this case, you can treat this part and do it. Yeah, that's also fine. What he's suggesting is, since we have, that's a good point, since we are ignoring the lambda for the NMOS, as I saw, anything that happens here has no bearing to what happens here. So I can just consider this separately, like this, right? And I can split Rx as 2Rx and 2Rx. So then you find the output due to only 1/2 and then get it. That's also fine. But if that is not clear, but if you followed my argument, that's okay. Okay. Either ways, you understand the final result. That's all that matters. Okay. So that is, yeah. So then let me. Okay. So now we know what is the tail node voltage. Let's get back to the calculation. So now let's try to find the small signal current IC. What is the current IC? What is the expression for IC? Gm of the NMOS times VGS, which is basically VCM minus whatever you computed. I think that was 2 GMN times Rx into VCM by 1 plus 2 GMN Rx times VCM. Oh yeah, sorry. Which one? Oh yeah. Okay, thanks. Correct. So what do you get if you simplify this? get GMN fine. Okay, so till this point it should be fine. So now let's quickly look at small signal voltages. So let us say I'll try to find this voltage here, V3. So what is the resistance looking here, R3? 1 over GM of which transistor? Is that fine? Gate and drain are connected. So any excitation you apply at the drain gets connected to the gate. So GM times the gate voltage gets drawn. So the impedance is 1 by GM of the PMOS. Okay, so let's say it's 1 by GM of the PMOS. Okay, so what is the small signal V3 in terms of the current IC and the resistor R3? In terms of R3 and IC, can you tell me what is V3? Huh? IC into R3 or minus IC into R3? Minus IC into the resistor, fine. So this is minus IC times R3, that is minus IC by GM of the PMOS. So what can you see if, so this is V3. What can you say about the current in this transistor in the direction I have marked? In terms of V3, what can you say about the current in this direction? It's a PMOS transistor, source is incrementally shorted. At the gate, there is a change by V3. What is the change in the drain current? GM times VGS. From drain to source, the current is always GM times VGS for both NMOS and for PMOS. Fine. So what is the current? They call it I4, whatever. In terms of just IC and in terms of IC, yeah. Okay, it's basically V3 times GMP. What is this equal to? Fine. So I find that I4 is equal to minus IC. Is this okay? Any confusion here? Lambda P is considered. Lambda P is not 0. Which one? R3, right? Yeah, okay, that's where I'm getting it. Let us say approximate to 1 by GM. Right? Yeah, you are right. Exactly, you are right. I'm getting at that same point. So let us say you made this approximation. So at least now I already know the point. So let me mark it here. This I know is just approximate. So everything is approximate. So I4 is approximately this equal to this. So if I assume R3 to be approximately equal to 1 by GM, this is the result I get. Okay. So then what can you say about the current in the bottom direction? That is also IC. So what can you say about the current flowing to the output? The short circuit current, if you measure, it's going to be 0. So again the common mode gain comes out to be 0, and that is because you have approximated this to be 1 by GM. Okay. The exact expression is going to be small, but since you made an approximation, that small number has been approximated to 0. Okay. So let's don't make this approximation and do the full thing. What I told is fine. See, you guys correctly pointed that the R3 here will also contain RDS of the PMOS. But if I don't consider it, it looks like the output voltage small signal is 0. But what I'm saying is that is not exactly 0. That is approximate because you made this approximation. Now we'll try to find out the exact Vout and see what is the result we get. Okay. So now I'll erase this. You already know this. So let's rewrite things quickly. So what is R3 exactly? R3 is what? RDS of the PMOS parallel with 1 by GM. Okay. So so if you find this, yeah, let's say this is this. So this, you simplify this, you get RDSP by 1 plus GMP times DSP. Okay. So now let's find V3 exactly. This is going to be minus IC times this resistance. This is RDSP by 1 plus GMP times DSP. Then what is I4 exactly? What is I4? Yeah, this is basically minus IC times GMP RDSP by 1 plus, I'll say GM times R. Okay, I'm not writing all subscripts. Okay, so now tell me what is the short circuit output current. This is not IC, remember this is I4, or I'll say minus I4. So what is the short circuit current if I find it? In terms of I4 IC, what is it? Minus I4 minus IC. Fine? Is that fine? The effective short circuit current, if I find it, that's going to be minus I4 minus IC. So let's calculate it. How much is that? Minus I4 is IC times GMR by 1 plus GMR. Minus IC is my total output. So what is the output current now in terms of IC? Check. Can you check the polarity? Should be minus IC by 1 plus GMP. Okay. So this is V out. Sorry, I out. So what is V out? In terms of I out, what is V out? No, I mean, let's say I know I out, right? In terms of I out, what is the output voltage? I know the total current that will flow out. So what is the total voltage? I mean, is it what I'm saying is I know the current flowing here. Okay. What is the total voltage then? Into RDSP. Fine. So let's write it. This is going to be minus IC into RDSP. Okay. You know, it's a bit messy, but hopefully the point came across. Is this okay? Okay, the idea is don't get confused. So remember that the model is this. For an OTA, the model is this GM and R out. Okay, you find the short circuit current like this. So in this polarity times the output resistance. Okay, again remember it's all Norton equivalent circuit, right? You have a Norton current and a Thevenin resistance. You find the total short circuit current in this polarity. That's what we did now. I short circuit this and find this current as I out. That is the Norton current times the effective resistance gives the total voltage. Okay. Yeah, so now this is the expression we get. So let's stare at this. I see that V3 is this and V out is this. How do they compare? They are same? They're exactly same. So that is an interesting observation we should make. Let me move out. So here, yeah, let me erase everything. Let's all cut it out. Yeah. Right. So now I see that V out is exactly equal to V3, right? But remember, the circuit as such was a symmetric circuit or asymmetric circuit? Asymmetric. But in this condition, it seems like the drain voltages are exactly equal. So now can you say if it's symmetric or asymmetric? So what has made the circuit change from asymmetric to symmetric now? No, we didn't change anything, right? The same concept. What happened to the input? Sorry? Yeah, as long as you feed in a common mode excitation, you see that both these nodes will be at the same voltage. So this is the another condition wherein as long as you have a common mode excitation, the actual circuit which was asymmetric to start with starts to behave like a symmetric circuit. So it's like having an unruly kid. So if you have a kid who is only where parents are strict only at home, the kid will start unruly in the school. If the teacher is also strict and the parents are also strict, then hopefully it will be fine. Same thing. Both sides you push in correctly, things will be proper. So yeah, so which means the moment you make this observation, we can actually simplify the calculation easily. So I know these two nodes are at the same potential. So what can I do? If you find two nodes having the same potential, what is the first thing that your mind tells you to do? I can basically short it. Nothing changes. So now you see that things have become nicely symmetric. So I can simplify the circuit like this. It looks like I have two PMOS transistors put in parallel. That's all. So I can simplify this like this. I'll say it's 2x because I have two PMOS devices. Again, the gates are connected, sources are connected, even the drains are connected. And what can you say about the NMOS transistors? They are also in parallel. So I can redraw it like this. 2x, and then this is. So as long as I have a case wherein common mode excitation is applied and I don't short circuit this, right? I mean, if I short circuit this, things are weird, but as long as I don't do anything crazy and only apply common mode excitation, this circuit will be symmetric. Then you can basically fold one on top of the other and this reduces to a much simpler circuit. So now tell me, if I have one transistor, let us say its conductance is GM. Now I have put two transistors in parallel. What do you think will be the effective transconductance? 2GM, root 2GM, GM by root 2, GM by 2. I have one transistor. I am saying that its transconductance is GM, right? That is, if I apply a VGS here, the drain current changes as GM times VGS. I take an identical copy of the transistor, make this connection. What will be the effective GM? 2 times GM, is this fine? So remember, here when I connect two transistors in parallel, the voltages are remaining same. VGS is same, VDS is same. So the expression for GM you should use is What is the expression you should use? No. You can use 2 GM by AD. See, there is nothing wrong in using any expression, right? So let us say someone suggested I do this. But if I do this, I know that ID is also changing. So you have to take into account 2 variables. So that's why a simpler thing is to just look at a case wherein the expression contains the parameter that remains constant. Here the thing that remains constant is VGS minus VTH. So you better use this expression. Okay. So now when I put 2 transistors in parallel, it is as though the width has become 2 times, GM has become 2 times. Believe it or not, this was a question asked to my friend for IMA interview. They told that GM has 3 expressions, what will you use at what condition? Because this is basic aptitude math question, nothing to do with circuit design, right? Cool. So now you know this is 2 times GM. So now tell me what is the looking in impedance exactly? Hmm? 1 over 2 GMP and okay, something comes. Okay. Similarly, this has 2 times GM. So now can you directly tell me what is this voltage? Yeah, actually this is RDSP or something else. Let me just take this question, sorry, this circuit. We'll just look at this and wrap up for today. Yeah, so now I will basically replace the circuit like this. So this transistor has 2 times GMN, and you know this impedance. So this is the yellow impedance, say some RD, and this is RX, and I'm applying VCM. So can you tell me what is V out directly? This is a common source amplifier. GMRD, right? Okay, if you don't know, okay, at least this point should be clear, right? If I apply signal at the gate and observe the corresponding output at the source, this is like a source follower. You know what is this? This is what is Vs in terms of VCM? 2 GM Rx by done. Now I know gate voltage, I know source voltage. What can I find? Drain current. What is the drain current? Yeah, GMN into whatever, VGS, right? If I find it VGS, that's going to be VCM by whatever this. You simplify this, you should get, what do you get? GMN by. So does this expression sound familiar to you? GM by 1 plus GMR times the input seems to be the drain current. Have you seen this somewhere in the course before? You guys saw voltage control, realizing voltage controlled current source using, yeah. This is how you realize a voltage controlled current source, isn't it? And then you take the short circuit current here, correct? I'm sure you've seen this, realizing all control sources using a transistor, and this is exactly how we would have realized a voltage controlled current source. And that's what you also have, right? So this is 2 GMN, I'm really sorry, yeah. GM by 1 plus GMR times A. And please try to kind of recollect results, because it is one thing to just put down all the incremental equivalent of each element and solve by KCL. That is very good to do. But if you want to grow one step higher, you try to remember some important results, right? I mean, it's not like don't randomly by heart things, right? Cool. So now you know ID, then you can find the output. Output is minus ID times RD, and you will get it directly. And the output, you can directly find it. It is minus 2 GMN RD by 1 plus 2 GMN. That's what you should get. Okay. Ah, great. I'll put this. So let's just quickly simplify this and move on, or actually we don't even have to, we can do it here, right? So let us say I have a case. Okay, let me copy this. Just give me a moment. Now let us say I have a case where GMRX is much greater than 1, which in this case is a reasonable thing to assume because this is the output resistance of a current source, which although is not infinite, will be, let us say, reasonably large. If this is much greater than 1, how can you approximate this as? Okay, yeah, okay, fine, VCM. If the source voltage is VCM, what can you say about the current here? Source voltage is VCM, the current there is, fine. What can you say about the current here? So what is the output then? Minus? Okay. So if you, take the full expression and kind of do this thing that 2 GMN Rx is much greater than 1, this is what you will get finally. And remember, our RD was basically 1 by 2 GM of the PMOS parallel with RDS of the PMOS by 2, and for all practical purposes, what can you approximate this to be? 1 by? Okay. So the common mode gain, you will find this to be minus 1 by 2 GMP2. Right? No, V out by VCM, right? It is basically the same change is being applied to both of them, correct? Common mode is basically average of the two. See, it is average, we call it fancy word and say it's common mode. So if you take the average, it is VC, right? VCM. So that's about it. I'll end here. So the bottom line, 2 points, remember, 2 points to remember. This circuit, although it's purely asymmetrical, if you ignore the lambda for the NMOS transistors, then for a differential mode excitation, where I had this here, yeah, if I have a differential mode excitation, then this is at 0, right? That is because these two voltages will not affect here, so this looks like a symmetric circuit. And the second thing is, if I look at a common mode case, that is, if the excitation given to the two sides are the same, it is a common mode input, then the overall circuit looks purely symmetrical. And in that case, you can reduce it like this. Okay. So the circuit should look like this, right? Nothing should be short circuited. This is all it should be like this. And if the same inputs are applied, then these two nodes will be same. You can go on short. Then you can reduce it like this. And of course, you can do the common mode gain calculations. I did it now. If at any point you are getting stuck, please redo it again. And one thing is to always remember some quick results like this. So it is always nice to remember this result. If I have a source follower and if you lambda is 0, then this is Vi. This is GMR by 1 plus GMR times Vi. If you remember this, rest can be cool. I'll stop here. We'll see.